Hello everybody and welcome to NPTEL online certification course on semiconductor devices for next generation field effect transistor, a physics perspective. This is lecture number 39 and the topic of the lecture is introduction to FinFET structures. So we have actually entered into the region where we are actually talking about next generation field effect, which means that we have finished with double gate. In our previous lectures we have taken bulk MOSFET, the physics behind it, and now we are entering into a new structure or a new device which is a field effect transistor itself known as FinFET. So what we will do in this week is I will introduce to the MOSFET, I will classify the FinFET, we will do some high frequency small signal modeling of FinFETs, we will do an equivalent FinFET modeling and then look into the device circuit co-design issues of FinFET with various examples. Why this is very important? Because now FinFET is the mainstay of most of the digital world, and many of the processors are FinFET based, many of the memories are FinFET based. So understanding it and understanding the equivalent circuit model for RF applications becomes important as far as this structure is concerned. So this will be the outline of the current lecture, and that is why we are using multigate FinFET. What is the meaning of FinFET structure, technology, scaling nodes and FinFET fabrication steps. You already are aware of the fact that in our previous discussions so far, though I have not tacitly explained to you, but most of you are aware of that as you move in technology node from a higher channel length to a much more smaller channel lengths, you end up having these second order short channel effects, right? And the rule of thumb is that more you are able to surround the channel, so more the gate has control over the channel, lower will be your second order effects. So one rule of thumb which people always follow is better control on channel by gate, right? This will be actually responsible for reduced short channel effects. So this is the mainstay or the main bottom line through which all the scaling processes have actually progressed. So we will look into all those steps and finally we will be looking into the FinFET fabrication process. Now let us come to the idea why we are using a multi-gate FinFET technology, right? Till now we were all using single gate bulk MOSFET, and then we went for a double gate bulk MOSFET, and we saw that in the double gate bulk MOSFET, for example, or even single gate, you did have short channel effects. When you reduce the dimension of the device, which means that when the drain and source are coming closer to each other, the threshold voltage actually shifts, threshold voltage actually drops down. Your subthreshold slope degrades, which means that your subthreshold slope is basically per decade change, right, in the drain current. If you do, then how much amount of gate voltage change you need to do, that is known as a subthreshold slope. So that has degraded, which means that so the typical value which you face for subthreshold slope is 60 millivolt per decade at T equals to 300 Kelvin for devices, and it actually increases to about 80 or 60 or 70. Now last problem is that the off currents increases, which means the leakage current actually increases, resulting in an overall decrement in the performance of the device. So if you look at the right hand side diagram, this one, right, this is plotted ID drain current versus gate voltage for log scale, and on the right hand side this is basically a long channel device and this one is a short channel device. So this is for the short channel which you see, and the black one is for the long channel device. Two things is very much visible to you. One is for short channel devices, when you have large gate voltages, the currents are relatively larger, right, and that is expected also because the drain current in any FET device is directly proportional to W by L, the width by length ratio. Now since your length has actually shortened down, and if you did not scale down the widths, then the current will increase. There are other factors also, but prima facie just by looking at the formula we could assume that thing is there. and the green one is for large VD, right, large drain voltage, and this is for a smaller drain voltage. And obviously a larger drain voltage will have a larger current, and therefore you see the green color curve is above the red color curve, and the black color curve's current is the minimum one. So the long channel devices have a reduced current capability. Now if you go on looking at this curve and you go towards the left hand side, then that gate voltage at which the current turns on actually starts. So there is a threshold voltage shift. The threshold voltage is this point, where that gate voltage at which the device started it giving its on current, right. So for example, for the black curve, which is the long channel device, this is it. For the red colored curve, we can say that it has shifted to the left, whereas for the green colored it has shifted somewhere here. So there is a shift in the threshold voltage, right, and this is primarily because of the short channel effect which you see. So if you plot threshold voltage versus channel length, you will actually see that there is a roll off, which means the threshold voltage actually rolls off for a reduced channel length. So this is your channel length and this is your threshold voltage. Threshold voltage actually decrements very fast. That is one thing, but you see one interesting point here. Interesting point is when Vg equals to 0, which means that your device is in the off state, you still have large currents here, right. Actually in reality this will be shifted somewhere here at this particular point, this x axis. So even when Vg equals to 0 volts, right, you will automatically have, you see, your long channel devices have a lower off current as compared to the short channel devices. And this is one of the major problem areas which you see. So the overall performance degrades, though your current increases, but so does your off current, and therefore ion by off ratio mitigates or becomes lower. One way of therefore overcoming this problem is what is known as a FinFET, right. So I will just explain to you what FinFET is all about and then show you the structure of the FinFET which is there. Typically many papers have reported that if you do sub 50 nanometer regime, if you do this scaling in this regime, then what you will do is that the conventional MOSFET, as I told you, will face many difficulties like del Vt, right, subthreshold slope, I off, which we have already discussed till now. Further than this, you will also have BT band to band tunneling current which is available to you. You will have Dibble effects, the drain induced barrier lowering, you have gate induced drain lowering, GIDL, and so on and so forth. So to solve this problem over a period of time, many researchers have worked on it and they came out with many solutions for that. One proposed solution was basically referred to as a thin body silicon on insulator MOSFET. This was a solution which people came up with. Then we had double gate MOSFET, which we have already studied in our previous lectures. This is double gate. So gate at the top as well as at the bottom. And then you have triple gate, and therefore triple gate MOSFET, and then extension of that is basically a FinFET. And I will tell you why the name FinFET is coming into picture, but I will try to explain to that. Now and among all these candidates, FinFET is considered to be the most eligible candidate sort of for current trends in electronic design. In fact, it has already within the industry where FinFETs are used. It is a very promising candidate because it is very robust and it has got a better mobility enhancement and therefore a larger current drive. Typically, I will come to that later on. I will show to you that typically FinFETs are also segregated into two structures. Soy FinFETs are shown to you, and you have got bulk FinFETs. So you have soy FinFETs and bulk FinFETs are available, and I will show to you in the next graph how this soy and bulk FinFET comes into picture. Advantage of bulk FinFET is that they have a low cost, right. So this is basically low cost and then low defect count, because you do not have an oxidation layer at the below, and so on and so forth. No floating body effect and so on. If you compare bulk with soy, then soy has got few advantages as well. It suppresses leakage. So its off state currents are relatively lower as compared to a bulk state, and it's basically low source to drain. Source to drain to substrate contact is low, and therefore high frequency operation for soy can be also achieved. Anyway, so we will come to that in much more detail when we see the structure per se, and we will see how it works out. So, what we have learned therefore is we have given you an idea about the basic idea of FinFET. Let me come to the structure of FinFET before I come back to soy and bulk devices. Now, we have already studied planar MOSFETs, right, and the left hand side is basically the diagram of a planar MOSFET, this one, where this is the source, this side is the drain, and you have the gate here, and there is a big, this white color, small white color is my oxide layer, right, and this oxide layer can be a high K dielectric, for example HFO2 and so on and so forth, and these are oxides which are basically trying to insulate the device from subsequent devices nearby, right. So, sort of an STI in a sense, and then of course you have a silicon substrate. Let us see how FinFET comes into picture. So, FinFET is basically a quasi 3D structure, right, quasi 3D structure, as you can see on the right hand side. This is basically a quasi 3D structure, right, and this quasi 3D structure, why? Because the source and drain is sort of raised now, and the channel is like this. So, the channel is in this direction, whereas in the bulk MOSFET it was a one dimensional channel which was flowing in this dimension. Now, the channel is basically flowing in this. So, if you cut the cross section along this plane, you will actually see the channel to be something like this. So, within the plane of your laptop or computers, this will be the channel. On the front side of your laptop screens will be the source, at the back side will be drain, and this square pillar will carry all the current from source to drain, right. And therefore, thin white layer which you see here is the oxide layer, which is the MOS layer oxide, and this is the STI, and then you have a silicon substrate here. So, this is basically a multi-gate device. Why multi-gate? Because now the gate which is a metal gate, this is a metal gate, and you will have drain contact, source contact here and drain contact here, or you can have a elongated contact in this direction like this, right. What will happen is, since the gate now is basically surrounding the channel in all the three directions. What are the three directions? This. So, where is the channel formed? Channel is this here, and then on the back side you will have the channel. So, it is basically three dimensional channel which you see, and all the three direction the gate is actually enveloping the channel, and therefore, the source drain region forms fin on the silicon surface, and therefore, it is referred to as a FinFET. Why it is known as a FinFET? Because it is almost like a fish. If you look, if you see this gate to be actually the body of the fish, then this happens to be the fin of the fish. They are perpendicular to each other, right, and it is basically a non-planar, a 3D transistor. Actually, the first FinFET was fabricated as a delta, also referred to as a depleted lean channel transistor, which was first fabricated in Japan by Hitachi, and these were the authors who were actually did it in 1989 approximately: Hisamoto, Kaga, Kawamoto, and Takeda. In 1989, they were the first person to actually fabricate these devices at Hitachi. However, in 1998, the first 17 nanometer FinFET was developed by Professor Cheng-Ming Hu, who is currently a professor in US, and he is referred to as a father of FinFET, but that is what reference is given to. And the first FinFET came into picture in this manner. So, you see how is it different from a planar MOSFET? Planar MOSFET, this is 3D structure, raised source and drain and raised channel, right. So, that is the main feature of these devices. Let me show to you a soy FinFET and a bulk FinFET you have already seen. I will show you how a silicon on insulator. So, if you have this as a silicon substrate, and then you have silicon dioxide, right, silicon dioxide, and then you have surrounding it by gate, and the fin will be somewhere in the middle. So, this is your metal gate, and this is your channel, and there will be thin oxide layer somewhere here, right, and this is the idea. So, this is referred to as height of the fin, right, and this is referred to as the width of the fin. So, the height of the fin is the longitudinal height which you see, and the lateral surface thickness is referred to as W fin, right, width of the fin. So, this gives you a basic structure of the FinFET structure. Now, if you let us look at the FinFET's current flow, right, you should be aware of how the current will flow in a FinFET. Now, if you apply a gate voltage here on the FinFET, maybe a positive gate voltage, let us suppose I have a p type substrate here, the substrate is, let us suppose, p substrate, and we apply a positive gate bias. As you are aware, this is the oxide layer here, right, this is the oxide layer, this is the source, drain and gate. So, there will be electrons which will be formed somewhere along this region. There will be inversion charge will be formed in this region as well as at the back side, which means that at the back side here, right, it will be formed, and it will be formed just under the gate. So, though your channel length is said to be source and between source and drain, the effective distance which you see is between the gate. So, this is the gate length which you see. So, this is the gate length which you effectively see here. Now, let us look at how so what is the total width, effective width of a fin device? The effective width is given by the thickness of the fin structure. This is the fin, this is the thickness of the fin structure, and this is the height of the fin. So, it is 2 times the height of the fin, because this side as well as the back side, plus width of the fin. Let us assume that the height of the fin is 50 nanometer and the width of the fin is 6 nanometers. The effective fin width W effective will be 106 nanometers. So, you see, simply adding an extra dimension, I have been able to add the effective width and therefore the current of the device. However, you can understand that the height of the device is beyond the control of a designer, because that can be increased or decreased, right. Beyond the point you can increase, because the structural stability will come under question. So, you cannot do that, and therefore, what you can choose is the width, right, and therefore, you can choose the width such that the required width as per the designer's requirement. However, please understand that when the width falls below approximately 5 nanometer, there is a quantum confinement effects which come into picture. So, you will have quantum confinement effects, quantum confinement effects when your W goes below 5 nanometer. What is the problem? The problem is then, not the problem, but the implication of this is that now the energy state becomes discrete within the region, and therefore, electrons can only flow in certain discrete energy states, E1, E2 and E3, and there will be less of scattering and so on and so forth, the current will increase. And typically, that is the reason if you want to go into quantum confinement, designing a 5 nanometer thin silicon is by itself a challenge. So, we will keep that in later cases. Now, as I discussed with you, the width of the device affects device imperfection such as source and drain series resistance, CLM, and channel length modulation and subthreshold conduction. Why? Because if you keep width very large, then the formation of inversion layer will be difficult, because the electric fields will be smaller. Similarly, if you keep the width very large, you typically have a reduced value of source and drain resistance, because larger the width, lower the cross sectional area, and therefore, the resistance is offered by the device. However, if you make the width larger and larger, you also end up eating away into the silicon area of the fabricated, and therefore, it is advisable to keep an optimal width available to you for all practical purposes. Channel length modulation phenomena is also, just like bulk MOSFET, is there even in FinFETs, and it is pretty difficult and not very easy to fulfill the areas of CLM. Another methodology which people did was, and this is quite interesting phenomena, rather than having a single fin as shown in the figure here, right, can we have multiple fins available? So, the gate actually goes through the whole device, but let us see how it looks like. If you look here, for example, let us look at the first diagram here, this one, you see this is a multiple device. These are multiple fins, 1 fin, 2 fin and 3 fin, and the gate is actually surrounding all of them together. So, if you give a single gate voltage, that same gate voltage is applicable to all the 3 fins, right. And as a result, what will happen is that those 3 fins will conduct current or whatever, they will do some amount of conduction of current and so on and so forth. and this difference between the two fin is referred to as fin pitch, right. This is referred to as fin pitch. What do I mean by fin pitch? Fin pitch is the distance between two fins, right. And quite an interesting, we will see in the later course of our discussion on FinFET, fin pitch plays a major role while discussing RF or high frequency modeling. But fin pitch is a designer dependent quantity which depends upon how much area you want to choose and how many fins you want to generate within the same gate area, right, and so on and so forth. There is a critical ratio of the height of the fin to the fin pitch, and this ratio has to be maintained across all the FinFET devices. So, how much height you keep and how much they are separated, right, that is quite critical in understanding, right. Since the gate is common to all the structures, actually I do not worry about electromagnetic any interference or any problem of an aggressor victim sort of network available here, because the same potential will be applied to all the fins, and as a result all the fins will behave in the same fashion. Now, because of the very small dimension of the intrinsic FinFET, typically the source drain contact, which is this one, the black colored which you see here, right, they are generally placed away from the core of the device. The core of the device is this one, and your source drain contacts are typically here. So, this is a two fin structure, this is a one fin or a single fin structure, and this is the gate. Let us suppose this is the drain, this is the source contact, this is again the drain contact, and this is the source contact, correct. And therefore, these contacts play a major role in talking with the outside world. Okay, let me come to the technology scaling nodes here now, and there are many process steps, there are many ways of processing. I will discuss this part of the lecture. Many process steps which are involved while designing a FinFET, and typically if you look at this point, we have the process name as 22 nanometer, HP means high power, 22 nanometer. 22 nanometer is the channel length which they are talking about. Then 16 nanometer, we have 14 nanometer, right, and we have again 14 nanometer high performance. So, this is HP is high performance, right, you have low power, right, and so on and so forth. The supply voltage which you see is 0.75, VDD is 75, 75, 0.8 and 0.7. The minimum gate length they have used is 26. So, you see the minimum gate length is 26, but the actual what they term when they put it in the market is we say 22 nanometer technology, right, and then we have got these values here and so on and so forth. What has happened is that this is slightly old data. So, basically Q4 of 14, already 14 nanometer HP has come into picture, high performance Intel chip is already available. Okay, so let me look at the FinFET commercialization. As I discussed with you, in 2004 Samsung demonstrated the bulk FinFET technology. They used it for designing FinFET DRAMs using 90 nanometer bulk FinFET process. 2011 Intel actually demonstrated a tri-gate transistor. In 2013 Hinds began commercial mass production for a 16 nanometer process, and 17 TSMC began production for memory design, SRAM design, static random access memory, using a 7 nanometer process. So, this is the overall technology flow, and we have discussed about the basic idea about FinFET. We have also discussed about how a FinFET looks like technically. I have kept the understanding to a bare minimum in terms of numerical analysis, but we have extended the technology scaling nodes for you, the commercial technology scaling nodes, for explaining what is a FinFET looks like, right. With this we will be finishing this lecture. In the next lecture we will take a fabrication and some high frequency modeling of FinFETs. Thank you.